Okay, this is what we were talking about last time. Booleans and Boolean operators. And we talked about not, which you all should be very familiar with, and, which you should probably already be very familiar with, and or, which you should also be very familiar with. And we also did take a moment to emphasize the fact that, remember how we talked a little bit? I mean, I kind of picked on you, but we emphasized the whole short circuit and short circuit or, meaning, if you know that, if it's false and, I don't really care what's on the other side of that operator. If it's false and anything, I know the answer is false. So we did hit that a little bit. But something I want to make sure I'm hitting really hard right now, that I didn't last time, and I want to make sure this is very clear, and or and not, okay? I'm explaining this to you right now, and you're like, yeah, I've known this for a while now. It's not too crazy. And yeah, okay, good. This is, and or not, is it's complete. How do I word this? And we're going to talk a little bit about some more fun stuff right now. But with and or and not, these three logical operators, we can even do it with less. We can do it with one, but you can do it with not and, which is, I know, it sounds like I said the same thing, but it's different. With these three things, we're going to build a whole computer. With these three logical operators, we can build a computer at an abstract level. Obviously, you're like, well, how do I physically we're going to get there. But and or and not, with and or and not, we can make, there's nothing else that your computers do beyond and or and not. Functionally, there's nothing else it can do. Everything you do is some massive combination of these things. But that's it. That's what this is all about, and or and not, okay? There are additional Boolean operators that we often talk about. Maybe I shouldn't say often, but we talk about. And the reason we talk about them is they are common enough that we'll refer to them as their own thing, but in reality, something like exclusive or, which I'll explain in a moment, can be made up of, you can make exclusive or with and or not, right? You put those together in a combination, you can make exclusive or. But we often like to talk about exclusive or as if it's its own thing just because it's, it's common enough that we refer to it as this thing. But really, it's actually a more abstract function or operation. So exclusive or, it's a binary operator, operates on two operands to produce a single value. Given Boolean values A and B, return true if either are true, false otherwise. But it's similar to or, but maybe I could reword that to be better. Because I say either are true, and I suppose it's somewhat ambiguous. If either are true. It can't be, yeah?
You can just stay with the line equivalent to. It's just one of them is true, but not both of them.
Yeah. One is true, but it can never be both true, right? And this is actually a funny thing, because usually, you remember doing truth tables? A, B, right? And if we do A or B, okay, we get 0, 0, 0, 1, 1, 0, 1, 1. Remember doing truth tables? If you didn't do truth tables yet, well, we're doing a truth table, right? And let's think about the different combinations. If we're doing or, and we see a 0 and a 0, well, that's 0. 0, 1, 1, 1, 0, 1, 1, 1, 1. But it's always funny. Every time, I'm teaching 161, let's say, and I'm introducing or. Always, there's some people in the room that are like, really, shouldn't it only really be? And that's right. There is actually kind of some ambiguity with language in English about okay, should it really include? So what we do to make it more specific, to be precise, we say or and then exclusive or. We go 0, 1, 1, 0. That's exclusive or, okay? One is true, but not both, or not neither, all right? So students, when they're learning OR for the first time, sometimes are like, what does he actually mean in terms of like, what would it do? This is OR, this is exclusive OR. All right? Yeah? Happy, sad? Cool? Cool. When looking at this, never mind, we'll come back to it. We'll get to there. Not OR is another really common one that we'll talk about. We talk about it as if it's its like own operation, but really at the end of the day, it's not an or it's or followed by a not. So not or would be like 1, 0, 0, 0. Not A or B, right? It's like two operations. It's like doing or and then nodding it, basically inverting all the outputs. But we often talk about it as if it's its own operation. Like we kind of like do the 2 and 1. Even though, yeah, it's the 2, but you know, we do the 2 and 1. Sometimes denoted like this, it's like this, functionally complete. With not or, you can actually implement not and an or. And if you can implement not and an or, you can implement anything. Meaning with this one operation, which is really two operations, with this one operation, you can actually build a full working computer. Similarly with NAND, not and. It's the same thing as and, but you invert the output. Common enough that we act as if it's its own single thing, even though really it's like made up of the two. Now, when I say it's made up of the two, it really comes from like my approach to it. If we start from the position of and, or, and not, I can be like, well, I can make not and with and not, right? But if I start from the position of not and is the only thing that exists, which is the only thing that really needs to exist, then I can go and implement not and or. It's really from which way am I approaching it? If we think of this as a single thing, then we can build and with several applications of not and. We'll see what we mean by this once we start playing around with logic gates. This is also functionally complete. In fact, it is common when fabricating like chips for your computer, like circuits, because it's easier to make like one configuration. Often what you see on the chips is just a bunch of NANDs configured. Like you don't see an OR gate, you don't see an AND gate, you don't see a NOT gate. You just see NAND gates configured in a way to build everything. Because it's easier to only make one type of gate and then configure them however you want. I really want to go back to the point I said we're like, well, not and. Really, it's two operations. It's only two operations if I'm coming from the starting position of it's not and it's and. Similarly with or, if it's not and it's or. You put those together, you get NAND, or NOR. But that only makes sense if I'm starting from the three, not and or. I can start with, like pretend nothing else exists and we just start with not and. With not and, I can generate everything else. We'll see an example of that. So here's not and, here's not or, and here is exclusive or in that fancy like set diagram type representation. Truth tables. Now I already showed you this. This is a nice standard structured visualization of all possible values for like these logical expressions. What's nice about truth tables is you can prove things about it because you can generate like an exhaustive proof. You can generate all possible combinations of how these operators would work, thereby like proving things about these operations and like what you would get by applying operations in a certain way. Because you generate an exhaustive proof. Like there's no ambiguity about what you would get. So here's a truth table, but instead of using zeros and ones, I'm using false and trues. Okay? So if I start with A and B, you'll notice with two different values, two different like variable values, let's call A and B variables. What values can they take on? True or false? How many combinations of two values do I have? 4, right? we can have false, 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 true, true, false, true, true. If I had 3 variables, how many combinations would I have? Come on, quick. If I had 4, how many? If I had 5, how many? How could you know so fast? Because you just double it every time. Oh my God. This is going to be a big pattern. Right? We see, okay, you just double every time. Yeah, go figure. Anyways. So if we start with A and B, false, false. Well, if we do not A, I really don't care about what the value of B is. So not A, well, if A is false, we get true. And then, okay, the not one's kind of silly because it only needs the A value. So what's not false? What's not false? What's not true? What's not true? That's that line. And then well, false, 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 true. It's only true if both A and B are true, or it's only false when neither are true. And then we have exclusive or, not and not or. So there are the truth tables. That is how these operations work. Questions about any of this? Do note that if I use 0 or 1, you should not be asking a question like, wait, what is he? It's the same. True, false, 0, 1, on, off, high, low. It's all the same. In general, mostly for brevity, I'm going to be using 0s and 1s. Maybe every once in a while I'll use a true or false, whatever. But 0s and 1s. Empty columns. Oh yeah, the empty columns here, I just provided them for visual clarity. They have no functional meaning in any way. They're just kind of like add separation, right? Here are the variables, or the values the operands can take. Here are the first 3 that we talked about, and here's the next 3 we talked about. I just kind of like added these columns for visual clarity, that's all. I've done a lot of stuff like that in this course where you might start to think like, does that have meaning? Like if you ever have a question, let me know. Because sometimes it's really just for visual clarity. Like something you definitely will see is like if I'm writing like sometimes if I'm writing like 8 bits, I've got like 0, 0, 1, 0, 0, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7. Sometimes like I will write it in a way where it's like 0, 0, 1, 0, 0, 1, 1, 1. Like I'll add like a little bit of a space there. All right? Just for the sake of like, okay, yeah, okay. Or sometimes like if it's 16, I might break them in groups of 8 or something, right? It's really just for visual clarity. It doesn't have any meaning. Hey, can anyone tell me really quick what value this is in hex? Come on, quickly, come on. Come on. Well, what value is this? 7. And what value is this? Oh, it's 27 in hex. Come on, remember? It's just you break it down into groups of 4. And this trick only works if it's like if the bases are even powers of one another. Come on, you should have had that. I'm teasing you, of course. Yeah, okay. So building out the truth tables. So notice that not and not or, they are, again, this is starting from the position that, let's start with, like the axioms we have are not and or. That's what we're starting with. Technically, we don't need to start there, but let's say they are. We can look at those and say, well, those are like compound operations. They're made up of 2 operators, not and or, depending on which one we're doing. So these columns are inverse of the basic operators in the table, that literally not those columns. So consider a more complex compound expression, like what do we have? A and not B or not C. Okay? There's nothing wrong with that. Now, if you ask me, what is the purpose of this expression? What is the functional meaning of this expression beyond what it literally is? There is none at this stage. It's just, I'm just saying, imagine I have this operation. How would I do it? Well, often what you're going to want to do for convincing yourself and providing an exhaustive proof, you can give me like we can show you all possible combinations of those three variables now. What do we have? Like, what do we get, right? So if you were to try to, what I'm saying is if I'm trying to do this all in one shot, don't. You're going to mess that up. Don't. And it's also like, if you skip steps, you're, like, remember the whole message, like how much of 161 and 162 was, computer code is for humans, not for computers. Make your code, make your work as clear as possible. If you give your code to someone and they have to go like, what is this? Like, what? This doesn't make, you messed up. Your code should be painfully obvious. If you can write the code in one line of code, if you can solve your problem in one complex line of code, or 4 very simple, easy to understand lines of code, do it in 4 simple, easy to understand lines of code because it's easier to understand. We show all our work so there's no ifs, ands, or buts about what's going on here. So how many rows do I have? Well, there should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Perfect. So what do we get? Well, I know that I need to know, I got to know what not B is, so I can AND it with A, and I need to know what not C is, and what the result of this is, so I can generate that full thing. Like, let's break it down into its parts. Well, what's not B? Well, that'll be easy. If B is 0, it should be 1. 1, 0, 0, 1, 1, 0, 0. 1, 1, 0, 0, 1, 1. Perfect. Looks good to me. What's not C? 1, 0, 1, 0, 1, 0, 1, 0. Okay, cool. So now that I know what not B is, and I already know what A is, how can I generate A and not B? Well, I go, all right, well, that's 0, 0, 0, 0, 1, 1, 0, 0. Was that right? Good. And I'm looking at, okay, this column and this column, and I'm performing AND. So I'm doing one step at a time. And then finally, the last one, and again, these blank columns have no meaning other than like visual separation. What are we doing here? Well, we take this column and that column, and we OR it. So we should have 1, 0, 1, 0, 1, 1, 1, 0. Looks good to me. Cool. Take your time. Build it out. Don't skip steps. If you skip steps, not only will you potentially make mistakes, it's far easier to make mistakes, but it's also less clear to anyone else looking at what you're doing, which is far more important than you realize. And again, you generate, like here it is. Why? Because that's literally every possible combination, as you can see. It's an exhaustive proof. There's no, like, if someone says, prove it better, you can't. There's no other way to show it. It's just, that's what it is. Here's a little activity. For the fun of it, this is not a lecture activity. This is just a do this. Build this out. Take a few minutes, do it right now, and we'll talk about it. It only has 2 variables, so you only need 4 columns. But do it. I'll give you like 4 minutes to do it. It shouldn't take you too long. This should be a review of discrete math. You're right. This is not wild. But who here has taken discrete math already? Who here has not taken it? Oh. All right, I guess you know more than I thought. Wonderful. Good to know. You're already pros at this. Who'd you have for discrete? Stephen? Is he the only one these days? Yeah? I wish they taught discrete in like high school. It's my high school used to. There used to be a class back in my day. There were more math options for like grade 12, and one of them was like geometry and discrete math was one of them, which was pretty cool. Who here's got an answer for the last column? Who here will in like 30 more seconds? Okay, take the 30 seconds. Compare with your neighbor to make sure you're all right. So who is bold enough to tell me what these four numbers are in order? 1110. Anyone else get that? Huh, could that have been simplified?
Yeah.
To what?
Well, you have not A or not B, or A and not B, so you did not B there kind of twice.
Okay. But like what operation was that last column in the end? It was not and, right? That's interesting. Huh. Okay, properties of logical operators. So there are like, when I say like algebraic properties, there's a lot of algebraic properties that we know are true for like regular integers, right? Like if you add 0 to something, you always get the same number back, right? These are like some of these properties, right? There is like the identity for operators, right? What's the identity for addition on like well, it's 0. Plus 0 does nothing. For multiplication, it's times 1, right? If you multiply something by 1, it stays the same. There's a lot of things like this. And here's a bunch of them. So the identity for or is or false. Anything or false will give you back, like A or false will always be whatever A is. Because an or false has no impact. False or false is always false. True or false is always true. So the or false is kind of like meaningless there. And in a similar way, and true, right? A and true will always give you back A. Idempotence for or is, well, A or A is always A. For and A is always A. The annihilator for or is true. You or anything with true, you always get true. You lose whatever. You annihilate whatever A was. Maybe it was true. Maybe it was false. Whatever it is, you don't know. Basically, what I mean here is, I don't care what A is. I know I always get back A. If I'm using the annihilator, I cannot tell you what A was. I cannot. This is not a one-way, like, I can't tell you what value was A. You would never know. You could never know. You'd have a 50-50 shot, right? Is that clear? The and one is and false. Associativity. This is kind of like, you know how like 1 plus 2 plus, like 1 plus 2 plus 3 is the same as 2 plus 3 plus 1, right? The order doesn't really matter. Same with ands. The order doesn't really matter. And this is kind of important because remember how last time I was talking about how sometimes we talk about like a 3-input and, right? But really it's just 2 ands. It's because of the associativity, okay? The order doesn't matter. Commutativity, order of where the operators are don't matter. Or sorry, where the operands are don't matter. Complementation, A or not A is always false. A and, pardon me. A and not A is always false. And similarly for or, but you know the opposite, A or not A is always true. And all of these should be obvious to you. And if they're not obvious, they can be if you put a little thought into it, right? And you can convince yourself by drawing out the truth table. And like, let's do a quick convincing of ourselves, right? Let's start with A. Well, 0, 1, right? Not A, 1, 0. If I and these, no matter how I and these two things together, I always get back false. No matter how I or these things together, I always get back true. Why do I always get false? One of them must be false. And if I and anything with false, I get false, as we can see from the annihilator.
And also, A can't be two things at once.
And A, well, it can't be because A is not A, yeah. Right? When you get to the more complex properties, they are often built with the less complex properties. Double negation, not A, well, that's just like inverting it twice. Not A is A, right? Distributivity, blah, blah, blah. My goodness. Distributivity of or over and. Well, if you have something like A or B and C, that's the same thing as doing A or B and A or C. Okay? If you don't believe me, draw out the truth table. You will convince yourself. Again, you will generate an exhaustive proof, eliminating all ambiguity. That's one thing that's really nice about Boolean operators and when doing this Boolean algebra, because there's only two possible values, right? Yeah?
You have a typo in distributivity over of and over not.
Do I? Where?
Or the first one, you have A and B and C. A and B or C.
A, B, A, C. A, B, A, where? Show me.
The left-hand side,
The left-hand side.
you should have A and you have
This is the right-hand side. Oh, you mean this one? Yeah.
No, the next one.
Ah, that should be that. Yes. You want to fix it? No? All right. Absorption. A or A and B, you get A back. Absorption 2, A and A or B, you get A back. Take a moment, think about this one. Convince yourself. Does that make sense? If you can't convince yourself like intuitively, very quickly, just draw it out. I might have these drawn out below. Do I? Absorption. Ah, okay. You know what? I go over that in a moment. And then De Morgan's. These are big, important ones. Have you heard of De Morgan's before? I'm seeing a lot of people nod. Good, good. It's an important one. De Morgan's 1. Not A and, or sorry, not A or not B is the same thing as not A and B. And De Morgan's will actually be part of the magic for how we get from like a universal set of like not and how you can generate everything from that. And De Morgan's 2, same idea, just, flip. De Morgan's is a cool one. So, if the absorption laws are unclear, consider the corresponding distributive and idempotent laws. For example, below is the first absorption law. A or A and B. Right? Now I'm saying look at the distributive and idempotent ones. So, distributive. Okay. If we apply the distributivity of or, okay, so that gives us A or B and A or C. Now here, where it's just A, so it'll be A and B or A, no, A or A. Oh, I'm getting tongue-tied here. My goodness. If we apply distributivity, blah, 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 A or A and A or B, right? Well, that's just A, right? We know that. And A or B, okay, well, that's where we go. Well, now we've actually just kind of like ended up back at okay, let's carry on. So if A is false, given the annihilator law, the expression evaluates to false. Right? Pardon? Did I say or?
No.
Oh, okay. I figure I am because I'm getting them all wrong today. What is written is probably more correct than what I'm saying right now. If A is false, given the and annihilator law, the expression evaluates to false. Right? False and like whatever, right? False and whatever, it's false. If A is true, given the identity law, the expression evaluates to the result of that, right? So true, like what I'm saying is if this is true and this part doesn't, I don't care, right? I don't care about true and because whatever the result of that is, it's going to depend, for and, it depends on what the result of this is, okay? And, well, if A is true, I just said, right? Given the annihilator law results in true, therefore the whole expression evaluates to true. This is a longhand wavy way of saying, when in doubt, draw out the full truth tables and you will convince yourself. And if you look at all of those properties, those algebraic properties along the way, you can kind of see how they feed into each other. Sometimes it's not like one necessary, there might not even be a directionality in how they feed into each other. They might be kind of like cyclical, but you'll convince yourself as you go. And here's the truth table for that. Right? Now, De Morgan's law. You've already learned this, but being aware of what time it is, I'm going to wrap up right now. Does anyone have any final questions before we end for today? Okay, I'll try to remember to fix that issue. If you send me an email, I'll definitely fix it. Send me the email. Ideally, you submit a pull request and fix it. Well, it'll take 2 seconds. Maybe I should do that at the beginning of next class. Take five minutes to show you how I'll really quick to fix all the typos, because there's going to be a lot. All right.